Wait,
Alex
let me.
and
Okay.
Angela. Can I start?
Yeah, hi. So, welcome to the IQIM seminar. Today we have Yuan Su, who is coming to us from University of Maryland, just starting his postdoc this fall. I think he actually managed to make it physically to Pasadena, which is great.
Yeah.
But of course, today with us virtually, and he's going to be talking about Trotter error and product formulas. So, take it away.
Thanks, Alex and Angela, for inviting me here for the virtual talk. So today I would like to say something about quantum simulation, about our recent work called a Trotter error, a theory of Trotter error. And this is a joint work, which is a collaboration with many people. So with Andrew Childs from Maryland, Ming Chuan from Maryland, Nathan Wei from Toronto, and Shu Chenzhu from Georgetown. Okay, so I included this slide here. I'm not sure if I really need this, but I guess we can use this to be on the same page. So basically, we have some quantum computing basics. The usual quantum circuit model. We can describe a quantum computation using quantum circuits, which contains elementary quantum gates. For example, we have this single qubit operations or single qubit gates. For example, we have this poly X, poly Y, and poly Z. And we also have this Hadamard gate, single qubit rotation gates, and also this T gates. So these are just single qubit elementary operations. Well, in general, you could have multi-qubit operations. So for example, if you have operation U and operation V, well, I guess you can put them together. You have U tensor V. But on the other hand, you also can have something like this, like the so-called C0 gate, which cannot be simply decomposed into tensor product of elementary gates. So in any case, in the usual quantum circuit model, you can describe a quantum computation using a sequence of elementary gates. And usually the complexity of such a simulation or such a computation will be quantified by the number of gates appear in these circuits. So there are many problems that you can consider to solve on a quantum computer. But in this talk, I will be exclusively focusing on one problem. So this is the problem of quantum simulation. So we know that the dynamics of a quantum systems are described by the so-called Schrodinger equation, according to the Schrodinger equation. So this is a first order differential equation. So let's say if the evolution operator is U, then the derivative of U is equal to the Hamiltonian times U. And there's also an initial condition here, so identity. Well, I guess in general, if this Hamiltonian is time dependent, then you don't have a closed form solution. So in this case, we can just formally represent the solution as a time ordered exponential. So we use this notation for time ordered exponential. But in the special case where this Hamiltonian is time independent, then you can actually have a nice closed form solution. So in this case, you have e to the minus ith, so just a matrix exponential. So in any case, the problem that I would like to consider in this talk is as follows. So you have a Hamiltonian, let's say h, and then you have an evolution time, let's say time t. And basically the goal is you just want to perform this e to the minus ith up to some accuracy epsilon, maybe quantified by the spectral norm, let's say. So this is basically the problem. It seems very straightforward. Basically, you just want to exponentiate a matrix, but actually it's quite difficult for a classical computer due to the growth of dimensionality. But on the other hand, the solution, an efficient solution of this problem could potentially have applications in many different areas. For example, people have been trying to apply the idea of quantum simulation to understand chemical reactions or to study material properties. And there are also some potential applications of quantum simulation to quantum computation itself. So for example, if you have an adiabatic evolution and you can try to implement this evolution on a quantum computer using ideas of quantum simulation. So there are also other potential applications to designing other quantum algorithms. For example, there's a famous quantum algorithms for solving linear equations. And some of the methods for solving linear equations also involve quantum simulation as a subroutine. So also has applications there. In any case, as maybe some of you might know, this idea of quantum simulation is also one of the original motivations for Feynman to propose this idea of a quantum computer. And nowadays people like to talk about near-term applications, and quantum simulation is also one of the original like potential candidates for near-term quantum device to solve. So, okay, so that's about quantum simulation. There are many algorithms that you can use on a quantum computer to do this quantum simulation, but perhaps the most simplest method is this method based on product formulas. Well, there are many different names referring to the same method. For example, usually people working in physics, like maybe some of us, would call it a Trotterization. There are also other people, especially like people working more on the mathematical side, like maybe numerical analysis, would call it a splitting method or operator splitting method. But I guess I'll just refer to it as product formula in this talk. In any case, the assumption here is that we have a target system, H, which is given as a linear combination of terms. So you have H, which is a sum over gamma, and then you have H gamma. And then you assume that each term can be directly exponentiated on a quantum computer. So for example, it could be a local Pauli operator. You can directly exponentiate that using elementary quantum gates. Okay, so under this assumption, what we can do is we can use a so-called first order Lie-Trotter formula. So remember, your goal is to exponentiate the sum of those operators, but maybe you cannot do it directly, but instead you individually exponentiate each term and then you multiply them together. So this is what I call first order Lie-Trotter formula. I guess in general, those matrices do not commute with each other. So you don't have an exact equality here. But instead, it will introduce some error. Let me call it a Trotter error. So this Trotter error is second order in T. So let's say if the evolution time is small, T is small, then this approximation is pretty accurate. But how about a larger T? So let's say if you want to simulate for a longer time, well, one thing that you can do is you can divide the evolution into R steps. And then you only apply this formula within each short step, and then you combine the results together. So each step you can get a fairly accurate approximation, and then you put them together, and hopefully you get a good approximation overall. So this approximation will be better and better if you choose R, the number of steps, to be larger and larger. I will have a more detailed analysis of this on later slides, but for now, let's just be satisfied with the outline of the algorithm. Okay, so that's basically about the simplest first order Lie-Trotter formula. Well, I guess a more generalized approach that you can consider is try to use more complicated formulas. For example, there's a family of formulas constructed by Suzuki in 1982. So I'll call it the Suzuki formulas. So in the simplest case, he constructed this second order formula, which looks similar to the first order case, except that we have two stages now. So in the first stage, we order the term in the forward direction. So we go from H1 up to H gamma. And then in the second stage, we order them in the backward direction. So we go from H gamma to H1. So it turns out that this can achieve second order accuracy. So the error will be third order. Well, you can start from here and recursively define higher order formulas. For example, you can define 2k order formula based on 2k minus 1th order. In this case, every time you do this recursion, you will have to multiply the number of stages by 5. So for example, second order, you have 2 stages. Fourth order, you have 10 stages, and so on and so forth. Okay. Well, of course, there are many other formulas, product formulas, but I won't be able to survey all of them in this talk. But maybe we can consider a general, I don't know, like the definition of product formulas. So let's say a general pth order product formula that I will be considering here will be something like this. So here I have 2 products. So the first products will go through all the stages. Like in the second order formula, we have 2 stages, go through these 2 stages. And the second product will go through all the terms, right? So we have 1 to gamma and gamma to 1. Of course, there could be some permutation of the terms. So I use this pi to control the permutation ordering of the terms. So this would be like a general form of the product formula. And let's say if it's a pth order formula, it will be pth order accurate. So the error will be p plus 1's order. So you have t to the p plus 1. Okay, so these are just.
Yuan, you said that the number of stages increases by a factor of 5 every time you increase p by 1. So It's like increasing exponentially in p. Okay.
Yeah, that's for the Suzuki construction. Of course, you can use other constructions. Maybe there will be different growth of the number of stages.
Okay.
Any other questions? Okay, so in any case, these are just simple mathematical tools that we can use for quantum simulation. And well, I should mention that beyond this simplest product formula approach, there have been many other approaches for quantum simulation. So here I have a picture which shows some of the simulation algorithms. It's a funny picture discovered by my co-author Ming. So for example, there's an algorithm based on truncating Taylor series. So you start from the exponential function and you do a Taylor expansion, you truncate it and try to implement it on a quantum computer. And there are also some other algorithms. For example, this algorithm called the cubitization algorithm, which manipulates the spectrum of the Hamiltonian in some 2x2 subspaces. We have this algorithm called quantum walk, and there are many, many other quantum simulation algorithms. Product formula is also in this picture, but she doesn't look very happy because somehow it turns out that this more recent quantum simulation algorithms have better asymptotic scaling as a function of evolution time and the accuracy over product formulas. So many people, especially like people working on the theoretical side of quantum simulation, have been in recent years trying to understand this more advanced quantum simulation algorithms instead of product formulas because they have better asymptotic scaling. But in this talk, I would like to argue that maybe this is not the right thing to do because actually, if you look at the empirical performance of doing quantum simulation, then in many cases, actually, product formulas could be advantageous. So for example, here I'm doing a simulation of a 1D Heisenberg model. So it's a 1D chain with nearest neighbor interactions. So for example, here I use this short notation to represent Pauli interactions. We have XX, Y1, ZZ. And also, we have this single Z operators acting on each one of the qubits. So I simulate this Hamiltonian for some small sizes and collect some numerical data. And this data is showing this picture on the right. Basically, if you compare the performance of different quantum simulation algorithms, you find that indeed, if you only believe the rigorous error analysis, previous analysis, then product formula doesn't perform really well. It has the largest gate complexity. But on the other hand, if you do the numerical simulation, you try to find out the empirical performance, the actual performance, then actually product formula becomes the best one to use. It has the least gate complexity. So there's a significant gap between what we can prove for the product formula when what's the actual performance. And this is something that we would like to try to understand in this talk, like how to close this big gap. Well, beyond this reason, there have been many other reasons why we need to continue to study product formulas. Also, somehow it has been de-emphasized in theoretical side of quantum simulation. So, well, this algorithm is very simple. It can decompose the evolution without using any ancillary qubits, as opposed to more advanced quantum simulation algorithms. So maybe there's this feature would be desirable for near-term implementation, where you will only access a limited number of qubits within one experiments. But on the other hand, product formulas can be very efficient, as we just saw in the last slide. Like the intuition would be that it can use the commutativity of the Hamiltonian. So for example, in the extreme case where all the terms commute with each other, then you can just, simultaneously diagonalize those terms. You can use its product formula without any error. So in general, maybe you can still speed up your quantum simulation by using this commutativity. Well, there are also some other nice features. For example, product formula seems to be a very straightforward approach. It can, in some cases, preserve the locality of the system, right? So for example, if you want to simulate a 1D system with nearest neighbor interactions, and you look at the quantum circuit, well, it also, in some sense, preserves the locality. So you have these red boxes corresponding to the exponential of the odd terms. And you have these blue boxes corresponding to the exponential of the even terms. And you have this kind of pattern here. And sometimes this kind of locality property can help you further improve your simulation. For example, if you want to simulate local observables. There are also other possible applications. For example, in some of the classical methods for simulating quantum systems, and also sometimes in areas beyond quantum computing. Okay, so I guess there are many aspects why we should continue to care about product formulas. I won't be able to talk all of them, but instead I would like to focus on one particular aspect, namely how product formulas can explore the commutativity of the Hamiltonian to speed up quantum simulation. And I guess that's basically, I want to talk about the background of this work. And I'm planning to go into some technical details of this work, but hopefully you can still follow me. Please interrupt me at any time if you have any technical questions or comments. Okay, so I guess I can start by somehow summarizing previous attempts towards understanding this problem. So there's a very famous formula in physics and mathematics. It's called a Baker-Campbell-Hausdorff expansion. So let's consider a very, very simple case where you only have two terms. So you have like the product formula, the first order formula will be e to the a, e to the b. Whereas the ideal thing that you want to do is e to the a plus b. Well, of course, there will be some error. So I just put the error in the exponent. So the BCH formula tells you that you can represent the error in terms of infinite series of nested commutators. So for example, in the second order, you have commutator of B and A. In the third order, you have BBA and ABA, and so on and so forth. Well, I guess I'm a little bit sloppy here because I didn't tell you about the convergence of this series. So it could be that sometimes this series could be divergent and you won't be able to get a good estimate. But let's assume that that's not the case. Let's not worry about that. And we assume that the BCH formula holds. And let's try to use this formula to estimate Trotter error. Sorry. Well, I guess there are many things that you can do. For example, one thing that you can do is you say, let's forget about all the high order terms. Let's only look at the lowest order term, this commutator of B and A. Well, this approach is very, very intuitive. Basically, you can try to get an understanding of the commutator by looking at this lowest order term. But it turns out that there could be some issues with the approach for simulating many systems. So for many cases, these higher order nested commutators turn out to grow very fast. So it can grow faster than the second order term, like this trade-off between T and the commutator. So actually, you won't get a very accurate estimate of Trotter error if you do this kind of truncation. Well, there are also other things that you can do. For example, you say, let's try to derive some tail bounds, right? So let's say whenever we encounter this commutator of B and A, let's just upper bound the norm of that by 2 times the norm of B and norm of A. Well, this can give you a very clean expression in the end, but of course, it doesn't use commutativity, so you also won't get a tight analysis for general cases. Yet another approach that you can consider is try to somehow do this summation in closed form. Let's say, try to compute this series directly. This turns out to only work for some special cases, like for example, systems with Lie-algebraic structures, but for other systems, actually you can't do that directly. So it turns out that unfortunately, none of the previous work will be useful for analyzing a general product formula for simulating general systems. But instead, there are some previous approaches that can help you analyze low-order product formulas. So for example, first-order formula and second-order formula. So here's a sketch of the analysis for the first-order formula. So remember, we are still looking at the simple case where you have two-term Hamiltonian. And in this case, the trick that will work is to instead look at the integral representation. So we see that this is a first-order Trotter formula, e to the A, e to the B. And then this is the ideal evolution that we want to approximate. And so this thing says the difference of these two things, like the Trotter error, is represented as double integral. And then inside this integral, you have a lot of exponentials, and then you have a commutator in the middle. So those exponentials will not be very important to us because if you calculate the spectral norm, they will disappear because they are unitary operators. So the only thing that matters is the thing in the middle, the commutator. So basically, let's say if you want to estimate the spectral norm error bound, then the only thing left will be like the thing in the middle of the commutator. Okay, so now we can compare what we obtain here from the integral representation with what we previously had in the BCH formula. We see that this new thing that we obtain exactly matches the lowest order of the BCH formula. But of course, here we did it in a rigorous way. We don't have to worry about all the higher order terms. So this gives you I guess in some sense, a better way of manipulating this kind of Trotter error expression. Okay, so this is for the simplest two-term case. Well, in general, you have a multi-term Hamiltonian, let's say gamma terms, but the analysis will be similar and can just invoke this kind of analysis recursively, and you get a general bound for the multi-term Hamiltonian. Okay, so this is an expression for the Trotter error. We can now use this expression to analyze the complexity of this algorithm that I promised you earlier in this talk. So this algorithm will be dividing the evolution into R steps and invoke this product formula within each step. So first we can do a triangle inequality. So let's say the error of R steps will be bounded by R times the error of one step. And then we invoke what we have for one step, and we have an expression like this. Okay, so now if we want to guarantee the simulation to be epsilon accurate, then what we can do is we can just choose a large enough R, say R is equal to a quantity like this. Then correspondingly, the gate complexity will just be the number of steps times the cost per step. So this will be R times gamma, because the final gate complexity of this algorithm. So that's basically about the analysis of first order Trotter formula. It's pretty tight because it matches a BCH expansion, the lowest order term. I can tell you that a similar bounds will also hold for the second order formula. That's another integral representation that you can use. But generalization to arbitrary product formula, higher order product formulas, was previously unknown before this work. But instead, what we prove is the following. We call it a Trotter error with commutator scaling. So let's say we start with a product formula. Let's say we start with a piece order formula. And we want to approximate the evolution of Hamiltonian, as is given by this linear combination of terms. Then my claim here is the error of the simulation, the Trotter error, will be asymptotically depending on this quantity called the alpha commutator. So this alpha commutator is defined as combination of all the possible nested commutators of P layers or P+1 layers, depending on convention. So, this is an argument about the error of the simulation, the Trotter error. But if you imitate what we had in the previous slides, you can derive an equivalent argument about the gate complexity. So if you do the conversion, you'll see that you need this number of gates to simulate Hamiltonian. And of course, the gate complexity will also depend on this quantity called alpha commutator. So this is a quantity that we need to understand if we want to understand the performance of product formulas. Well, some immediate observation. Well, this quantity is symmetric with respect to the ordering of the terms. So actually, if you only care about the asymptotic scaling, then you don't have to worry about the ordering of the term. It will give you the same asymptotic scaling. But of course, if you, let's say, want to do a near-term simulation, you care about the constant prefactor, then of course you should choose the optimal ordering of the terms. Well, this is an expression for the additive error. We just take the difference between these two terms. You can work out the bounds for multiplicative error, and also this is a real-time evolution, has imaginary time evolution. Although I won't show those bounds in detail in this talk. You can check the paper for details. So that's basically the main results of this work. And in the following, I would like to present some concrete examples.
Yuan, can I pause here for a second? So sure. I just want to make sure I understand. So the you have all the orderings of the H's here. So I guess there's gamma to the P terms in this sum for alpha tilde, but then in the complexity, you raise it to the 1 over p.
Yep.
So if these, like if h's are coming from a local Hamiltonian, each of the h's has bounded norm, then each of these terms will be constant, and this will give you like a nice, just proportional to like gamma squared or something in the number of gates. Is that?
Yeah, so if you just do this thing naively, you get gamma to the p plus 1's power. So you get something like gamma to the p plus 1 over p. So this is when you do it naively. But if you Hamiltonian has some commutativity property, then you can get a much smaller commutator from this expression, and you get a much smaller quantity here. So this will give you a better gate complexity in the end.
I see. So you start with this formula, and then the next step would be to look at the specific Hamiltonian you're considering and try to bound the commutators for that Hamiltonian.
Exactly. Yeah.
Right. Okay.
Yeah. Okay. So basically, this is the result that I would like to present, and in the following, I guess maybe I can talk about some applications and we found in the work, and I also want to tell you some ongoing work and maybe some possible directions for future work, and hopefully you can get a sense of how these formulas can be used in practice. Well, the first example that we have in mind is this simulation of nearest neighbor lattice Hamiltonians. We have seen an example of this in earlier slides. This 1D Heisenberg model, but in general, you can consider more general setting. For example, we have a 1D spin chain, and then we have nearest neighbor interactions. This kind of Hamiltonian models many physical systems in, let's say, condensed matter physics, nuclear physics, and quantum field theory. So people have been trying to understand the complexity of doing this simulation, let's say, using product formulas or other approaches. So there was a previous claim saying that people can actually simulate this kind of lattice Hamiltonian, let's say n-qubit Hamiltonian for time t, and the gate complexity will be something very close to n times t. So n is the size of the system and t is the evolution time. Well, what we found is that we can actually use this new analysis to give a justification of this claim. Well, remember, like the important quantity that we need to understand is this alpha computer. So let's try to do that. By definition, is given by this nested commutators. Well, we can further try to simplify this nested commutator. So we can start with the innermost layer, this h gamma 1. It has n choices or n minus 1 choices, depending on our convention. But in any case, if you fix one particular choice and you ask how many number of terms don't commute with this one, there are only constant number of them because you have nearest neighbor interactions. You can ask the same question. So how many number of terms of this h gamma 3 don't commute with the inner two operators? Well, there are also constant number of them. So as long as you fix a particular product formula, and you will always have constant number of choices for each layer in your nested commutator. So in the end, the only contribution that involves system size dependence will be the innermost layer operator. So the size of this nested commutator will grow asymptotically as something like O of n. So, following the standard arguments, you can work out the gate complexity of this product formula. And indeed, the gate complexity will be very close to n times t. So it justifies the previous claim. And combining with the previous lower bound, it also gives a simple, nearly optimal approach for simulating lattice Hamiltonians. Okay, so the second example that I have here is a simulation of electronic structure Hamiltonians. So in this case, well, I guess you can write this Hamiltonian in different ways. So for example, you can write it in different bases, in first quantization, second quantization. Here I'm considering a second quantization representation of plane wave basis of electronic structure. So in this case, the Hamiltonian is given as something like this. So you have some fermionic creation annihilation operators. You have some occupation and number operators, and some linear combination of them. Okay, so an efficient solution of such an electronic structure simulation turns out to be helpful for designing catalysts and materials. So, people have been trying to understand how to use quantum computers to speed up the simulation of such Hamiltonians. So the best previous results for simulating electronic structure in this setting, a second quantized plane wave electronic structure setting, is algorithm called the interaction picture algorithm, developed by some of the people who are working at Microsoft. So let's say if you want to simulate n spin orbitals, and let's say if you want to simulate for time t, then their algorithm will have a complexity that is very close to n squared times t. But the downside will be that their algorithm is complicated. People believe that if you actually implement that algorithm on using quantum circuits, you probably will have a large prefactor in terms of the gate complexity. But of course, the natural question would be to ask what happens if you want to use product formula. Well, first of all, if you want to use product formula, you have to exponentiate the elementary terms. Well, like the last two groups of terms here, they are occupation number operators, so they commute with each other, so you can directly exponentiate them without any error. But the first term here is a little bit tricky because you have general fermionic operators, and they do not necessarily commute with each other, but it turns out that you can resolve this issue by looking at the coefficient, right? So although you have two indices, j and k, the coefficients only depends on the difference of k and j. So you have k minus j here. So in other words, it's more like a translation invariant coefficient matrix. And this can be diagonalized by the Fourier transform. So in this case, we're using a fermionic version of the Fourier transform. And we can diagonalize that with some commuting terms. So you can directly implement using product formulas. And the remaining thing is just like the old strategy. We try to understand how this alpha computer scales, and then try to apply some standard arguments to work out the gate complexity. And the result will indeed be something like n squared times t, very close to that. And it's slightly worse than the interaction picture algorithm, but the advantage will be that product formula is very simple. So hopefully it can perform well in practice. And this also confirms a recent study from the numerical science by some of the people from Google's group and other groups. Okay, so the third example is a simulation of k-local Hamiltonians. So in this case, you have a Hamiltonian, which is given as a linear combination of terms. And each term acts on k qubits, so k is constant. Well, this model is very common in physics, and people have been trying to understand how to use quantum computers to simulate this kind of Hamiltonians. Well, the best previous approach to simulate this kind of k-local Hamiltonians is an approach called a cubitization algorithm. I won't be able to talk about the details of this algorithm, but it turns out that the complexity of this algorithm depends on this quantity called the one norm of the Hamiltonian. It's basically the sum of the magnitude of those terms. So you first take the spectral norm of each term, and then you sum them up. This is called a one norm. So again, we can ask, what about product formulas? Well, the old procedure, we can try to first compute this alpha commuter, given that it's nested commutators. We can use some commutativity to simplify this and work out the gate complexity. Well, it turns out that the result will almost depends on this quantity. So this is a 3 vertical line norm. It's called an induced one norm. So it's different from the one norm in that when you do this norm, you actually fix one particular index in your summation, and you only sum the remaining k-1 indices. So this induced one norm turns out to be smaller than the one norm, and the gap can be significant for many k local Hamiltonians. So in this case, if you actually switch to product formulas, you can get a better quantum simulation in principle. Okay, so the next example is a simulation of rapidly decaying power law interactions. In this case, you have Hamiltonian given as a sum of terms, and the strength of those terms will decay according to some power law. So, for example, the strength, the spectral norm, will be something like 1 over distance to the power of alpha. Let's say we are looking at a d-dimensional system. Examples include, for example, dipole-dipole interactions and van der Waals interactions. And you know, this kind of systems, the interaction strengths are decaying so fast that you actually exploit the locality of the system to speed up your quantum simulation. So the best previous algorithm for simulating this kind of systems is an algorithm using ideas of Lie-Robinson bounds. And the gate complexity will be something like this. So you have NT here, and the exponent will be 1 plus 2D over alpha minus D. This is the gate complexity of using Lie-Robinson based algorithm. Well, we can ask what happens if we use product formulas. Well, again, because the interaction strength is decaying so fast, we can actually do better than a naive application of product formulas. So the best strategy turns out to be to first do a truncation. So you first truncate at some cutoff value, L. This L is chosen so that the truncation error is below epsilon. But for this truncated Hamiltonian, you can basically apply the same procedure. You calculate this alpha commutator and then further calculate the gate complexity. And you get something like 1 plus D over alpha minus D, very close to that. So if you compare this exponent with previous one, this Lie-Robinson based algorithm, so this 2D over alpha minus D here is almost improved to this D over alpha minus D. So again, if you use product formulas, you can hopefully get a better performance for simulation. Okay, so I can quickly present some of the remaining examples. For example, you can also consider clustered Hamiltonians. In this case, your Hamiltonian is acting on n qubits, and you group the qubits into different groups. So you have strong interactions within each group, and then you have weaker interactions between different groups. So this is called clustered Hamiltonians. It's useful for in some of the classical methods for simulating large molecules. So there's results that designs hybrid classical quantum simulator for this kind of clustered Hamiltonians. And the algorithm also uses product formulas. So we are able to apply our new analysis to improve the runtime. Another application is to the simulation of transverse field ising model. In this case, you're actually not looking at a quantum simulation anymore, but a quantum Monte Carlo simulation. The goal is try to approximate the partition function up to some multiplicative error. And there are some previous algorithms designed by Bravi and Bravi-Gossets. You know, they have this Monte Carlo simulation, and they use product formulas as a subroutine in their algorithm. And again, we're able to improve their runtime by using this improved analysis. You know, although the resulting algorithm is doesn't look very practical, at least we have a big improvement in the absolute sense. So we have been talking about simulating evolutions in general, but let's say if our task is not so general, let's say we only look at the local observable, then actually you can do something better. So we're able to show that you can use product formulas to simulate local observables for power law interactions with a complexity that is independent of the system size. And this as a side results will imply a Lie-Robinson bounds nearly matching a Ricin bounds developed by me and some other people. Okay, so we have been talking about the asymptotic scaling, but I guess one of the original motivations for studying product formulas is a significant gap in the numerical simulation. So we did some numerical simulation for the 1D Heisenberg model that I presented in one of the early slides. So the result is that it indeed performs pretty well. It improves over the previous analysis by a very large amount, and it's also pretty close to the actual performance, only loses by a factor of 5. And this suggests that maybe we now have a quite good analysis of product formulas for both asymptotic scaling and also constant prefactor.
Sorry, what was the Trotter number in relation to the?
Oh, Trotter number is the number of steps.
The number of steps.
The gate complexity will be Trotter number times the cost per step. So you have R times whatever you have for one step.
Okay.
Does that make sense?
Yeah, that makes sense.
Great. Let me maybe make a very brief summary. In this work, we try to develop some mathematical tools for analyzing Trotter error and apply them to analyze the simulation of some physical systems. So specifically nearest neighbor lattice Hamiltonians, giving a nearly optimal way of simulating lattice Hamiltonians, very simple approach. For simulating electronic structure Hamiltonians, nearly matching the interaction picture algorithm. For k-local Hamiltonians, outperforming the qubitization algorithm. For parallel, rapidly decaying parallel interactions, faster than the Lie-Robinson based algorithm. We have some results for simulating clustered Hamiltonians, quantum multicolor simulations, also some new results for simulating local obstacles. So behind this thing is some mathematical tools that we developed for analyzing Trotter error. I won't be able to present all the technical details, but hopefully you have time to check out the paper and maybe you can find new applications beyond what has been listed here. So I want to maybe take 2 or 3 minutes to say something about some of the recent work that has been done after the release of this Trotter error paper. So one thing that we can further improve the performance of simulation is try to use symmetries of the system. For example, usually Hamiltonians arising in physics can have symmetries. So you have some operators that commute with the Hamiltonian. For example, in the Heisenberg model, you can rotate each qubit along the z direction with the same rotation angle. You can keep the Hamiltonian invariant. So this kind of symmetries can preserve the evolution, ideal evolution, but its effect is that it can rotate the error of the simulation into different directions. So if you perform R steps, you can rotate the error into R directions. And if you add them up, the hope would be that you can cancel the error destructively, so you can get a better quantum simulation. So a picture would be something like this. You insert some green boxes so that you can use the symmetry to speed up quantum simulation. Another thing is maybe you can use the information about the initial state, right? So we have been considering Trotter error quantum simulation in terms of spectral norm. So this is a worst case. It maximizes over all the initial state. But of course, you can also exploit the initial state to speed up your quantum simulation. So in practice, people often prepare a low energy initial state in the beginning and they do the simulation. So hopefully your performance will be much better if you exploit the initial state information. So we have ongoing work that attempts to address this problem for electronic structure Hamiltonians. And the result is qualitatively illustrated in this picture. Let's say if you only exploit the commutativity, you get like a blue curve, which doesn't perform well in the low energy regime. On the other hand, if you only exploit the initial state information, then you won't perform very well in the high energy regime. But instead, the new idea would be try to simultaneously exploit two sources of information, and you get this green curve, which is better than the previous two things. So there are also some other directions for future work. So for example, we have been talking about time-independent Hamiltonian simulation. Well, in general, you can look at time-dependent case. You will have simulations that is applicable to understanding quantum control schemes and many other applications. So it will be interesting to see whether this can be generalized. We have some generalized product formulas. So for example, it depends on divide and conquer idea, randomization idea, and also linear combination of unitary isings. So it will be interesting to see whether this kind of generalized product formulas can also be improved using commutativity of Hamiltonian. Some concrete circuit implementation for physical systems. Several weeks ago, there's a talk on simulating quantum field theory. So it'll be interesting to further explore circuit implementation. Some numerical implementation of this Trotter error bounds, try to derive some concrete resource estimates. Different cost metrics. So we are using quantum circuit model. So the number of gates determines the gate complexity. But maybe you can use a more physical motivated model, like some reason interest in sub-circuit model. Hopefully you can get advantage there. Simulation of low energy states. Maybe you can further use this energy information to speed up your quantum simulation beyond what we have been done here. Simulation of, in terms of noise, more realistic issues. And maybe there could be some other applications beyond what has been listed here. And with that, we have a very happy ending, and thanks for listening. I'm happy to take some questions.
Okay, great. Thanks, Yuan. So remember, if you have a question, you can type it in the chat, or you can raise your hand and we'll let you say your question out loud. But in the meantime, so I had one sort of question. So you mentioned as a follow-up this idea of like using the symmetry to have the errors cancel out.
Yep.
Could it also be the case that like if there are no symmetries and if it's like a chaotic evolution, then you'll get like natural cancellation of these errors instead of adding linearly? Is that something you would expect, or?
Yeah, it could be. So for example, it could be the case that if you are simulating some systems and you just use product formulas and the error just won't be able to add up destructively, you get the worst error accumulation. That could be the case. So
you do think that like the sort of worst case constructive adding of errors is like would that be like a typical outcome for some of these applications that you're considering, or do you hope that the errors might not add that badly?
Yeah, I guess usually for like this kind of spin systems, you will have some kind of symmetry that you can use. Mm-hmm. But maybe for systems in quantum chemistry, we haven't been able to find how to find symmetries to speed up this kind of quantum simulation. And also there's an issue here because actually if you use this symmetry, you have to introduce some additional gates like the green boxes. And this actually will increase the gate complexity of one step. So like you have to find a trade-off. On one hand, the symmetries can help you reduce the simulation error. So we'll have fewer number of steps. But on the other hand, the cost of implementing each step will increase. So there will be a trade-off.
Okay, that makes sense. All right, looks like we have a question in the chat. I'll read it and then you can answer. So Richard says, very nice talk. I have a basic question concerning the actual constant in your main result. How do you search for good term orderings in practice?
Oh, that's a good question. So I guess right now we don't have a systematic way of searching the optimal term ordering. So sometimes you can use some intuition to help you get a good ordering. For example, if you have a nearest neighbor system, so maybe the best strategy would be try to reduce the number of layers, like the depth of the quantum circuits. For example, if you have this, maybe you just group them into two groups. You have odd group, all the odd terms and all the even terms. So, this kind of ordering minimize the depth of the quantum surface. So maybe this could be a good ordering. But in general, we don't have a strategy to determine the optimal ordering yet.
Cool. Well, I guess it's now noon. If there's any last second questions, say them now. Otherwise, we'll be gathering in this virtual space after the talk, and I will post the link again. And we can all, anyone who's available, we'd love to talk to you afterward.
Okay. Thanks very much.